There are other reactions that the acid derivatives will do, and one of the first things we're going to look at is reduction by lithium aluminum hydride. Lithium aluminum hydride is an aggressive reducing agent, and it will reduce everything. What differs is what the product is. Those acid derivatives that do not have nitrogen in them are reduced down to alcohols. And when we take something like the ester or the anhydride that have two carbon chains, both sides of the anhydride or ester are reduced down to alcohols. Those functional groups that have nitrogen in them that are acid derivatives, those are reduced down to amines. Let's look at some examples. This is an acid halide, an acid chloride. Lithium aluminum hydride reduces it down to an alcohol. Here we have an anhydride, and notice there's two carbon chains, one on this side, one on this side. Both are reduced down to alcohols. Here we have an ester, and again, two carbon chains, one over here and one over here. It's cleaved in half, and you get two carbon chains attached to the alcohol. You have both sides reduced down to an alcohol. Here's a nitrogen-containing functional group. It's reduced down to the amine. And notice it does not cleave the chain. Any alkyl group that is attached to the nitrogen stays on the nitrogen. That's different from the oxygen-containing functional groups. If we have a nitrile, it's reduced down to the primary amine. So you tell me what's going to be the outcome of this reaction. Well, essentially, when you use lithium aluminum hydride on this, what happens is it bites off the carbonyl. You end up getting a ring without any carbonyl on it. Notice the carbonyl is reduced down to a methylene group. It's rather interesting, the mechanism, how this comes about. Basically, you reduce this down to an alcohol, and then you can have the nitrogen can leave temporarily, and it reforms that into a carbonyl aldehyde, which then is attacked again by the nitrogen, and it forms the imine, which then is reduced down to the amine. You don't need to realize all that, but what is important is that this gets reduced down to a methylene group. No oxygen is left, and there's no cleavage of the bonds on the nitrogen. What's the outcome of this reaction? Again, we get an alkyl on both sides of the nitrogen. The nitrogen carbon bonds are not broken. What is the outcome of these reactions? Well, here we have lithium aluminum hydride reducing an ester. Remember, when it's an all-oxygen functional group, you cleave the two carbon chains. So we get this alcohol and this one. Again, here we cleave the two carbon chains. So this gets cleaved right here. So what happens? This becomes an alcohol right there, and that becomes an alcohol right there. Be sure and count your carbons when doing ring compounds or even long chains like this. Make sure you don't add or lose carbons. It's very easy to do. What's the outcome of this reduction? Again, no nitrogen, so it's going to be reduced down to an alcohol. We have a reagent called DIBAH, which stands for diisobutyl aluminum hydride, and it is a less aggressive reducing agent. It's even less aggressive than sodium borohydride. It's less aggressive because it's hindered. And the two isobutyl groups on that aluminum make it so that it's harder for that hydride to be given up. Because it's less active, it will take acid derivatives to the aldehyde. Sorry, my brain stopped for a minute there. Because it is less active, it will stop in the reducing stage at the aldehyde. So when we use this on esters and on nitriles, we actually reduce them down and stop at the aldehyde stage. Now, nitriles naturally will go to an aldehyde because there's no other attachment to the carbon. There's only one chain on the carbon of a nitrile, one chain on the aldehyde. But esters have two chains. So when an ester is reduced down to the aldehyde, there's an alcohol that gets cleaved off. And so you need to realize that, because that alcohol chain is important and may be important in the compound that's formed. So let's look at this. Here we have an ester. When we treat it with DIBAH, what happens is the side with the carbonyl becomes the aldehyde, and the alcohol side gets cleaved off. Here is a nitrile that just gets converted directly to an aldehyde. So you determine what is the outcome of these reactions. Well, here we have an ester, and we're using lithium aluminum hydride. So what will happen, this gets cleaved, and we get an alcohol group here, a primary alcohol here, and a primary alcohol there. Methanol, and then the chain here is converted to an alcohol. This carbon used to be this carbon. If we use DIBAH, what happens? The two chains get cleaved again, and we're going to make methanol again, but instead of this being a primary alcohol, now it is an aldehyde. Look at this complicated molecule. What's going to happen when we use DIBAH? Well, DIBAH is just going to take that nitrile to the aldehyde. There are some other reactions that you need to know about. Let's look at the Grignard reagents and also the Gilman reagents. Acid derivatives will react with Grignard reagents in the same way that esters do. If you recall, a Grignard reagent will attack an ester 2 times. First time, it changes it into a tetrahedral intermediate, and the alcohol side of the ester leaves as a leaving group, which forms a ketone, and then the Grignard attacks again, and so you get a tertiary alcohol. If you have an acid derivative, you have just as good a leaving group, a halide, and what happens is the Grignard reagent will add twice, once to eliminate the chloride, and then the second time to change the carbonyl to an alcohol. Nitriles will react with Grignard reagents only once and convert a nitrile to a ketone, with that Grignard carbon chain being on the other side of the carbon. The original chain stays on, plus a new Grignard reagent chain. And then we have acid halides that can react with Gilman reagents. Remember, Gilman reagents were coupling agents, and that's essentially what they do here. The chloride comes off the acid chloride, the Gilman, the copper, lithium, and the other alkyl chain come off of the carbon chain, and you couple those two things together. So let's look at this so we can see it more clearly. Okay, here is an acid chloride with a Grignard reagent. It adds once to form a ketone, but then it's going to add again and give you an alcohol. Here's an ester. It does the same thing, adds once to give you a ketone, and then it adds again to give you an alcohol. Here's a nitrile. It adds once and stops, and then when you hydrolyze it, it turns it into a ketone. Here's an acid chloride, and a Gilman reagent. It couples. It takes this R group off the copper lithium agent and takes the chloride off and tacks the two together, and you get a ketone. So now go ahead and try to practice what you've just learned. We have an ester here with hint 2 phenyl magnesium bromides. What would be the outcome of this reaction? It's going to add twice, and we're going to end up getting this tertiary alcohol. So what is the outcome of these reactions? Well, here we have an acid chloride and a Gilman reagent. What's going to happen? You're going to get coupling. Here we have an acid chloride and a Grignard reagent. What's going to happen? It's going to add twice. Of course, with this, we'd have to have an acid wash to protonate that oxygen there, so this really is incomplete in what's listed, but you get the idea. So what is the outcome of vinyl magnesium chloride with acetonitrile followed by an acid wash? Well, here's acetonitrile and vinyl magnesium chloride. Because this is a Grignard reagent and a nitrile, you're going to have one attack, and then after the acid wash, what happens is it takes that adduct and changes it into a ketone. What is the outcome of gamma-butyrolactone with ethyl magnesium bromide? The gamma-butyrolactone is shown right here. Well, let's write down gamma-butyrolactone reacting with ethyl magnesium bromide. It's an ester. So once you have an adduct of the ethyl magnesium bromide doing a nucleophilic attack here, you get the tetrahedral intermediate, and then this part is eliminated, and you end up with a ketone. But that's susceptible to nucleophilic attack by the Grignard reagent again. So what happens? We end up getting a second adduct. So now we have an alcohol here and an alcohol here after protonation with an acid wash. So what is the outcome of lithium aluminum hydride with acetonitrile followed by an acid wash, and lithium aluminum hydride with succinic anhydride followed by an acid wash? Well, here's the acetonitrile and lithium aluminum hydride followed by an acid wash. This is going to reduce this down to the amine. Notice, count your carbons, 2 here, 2 there. What about the succinic anhydride? Well, it's going to reduce it down to the diol. And you can see 4 carbons, 4 carbons. This is reduced down all the way. What is the outcome of gamma-butyrolactone with lithium aluminum hydride? Again, that's going to cleave this and reduce it down to the alcohols. So we end up making the 4-carbon diol. Here, this is different. Remember, if it contains a nitrogen, you reduce it down to an amine and you do not cleave any chains. So we reduce it down to this secondary amine.